Hey everyone, it's Justin again. In this lesson, we'll discuss the Fibonacci sequence and discover its many interesting applications. This spiral is making me, very dizzy, so let's hurry up and get started. By the end of this lesson, you should be able to find the value of specific terms in the Fibonacci sequence. You should be able to recognize Fibonacci-style patterns in real-world applications. First, we'll discuss the Fibonacci sequence. Next, we'll discuss the Fibonacci spiral and the golden ratio. And finally, we'll discuss more applications. The Fibonacci sequence is an interesting sequence that you may have encountered previously. It's defined by the following formula. Notice that there are two previous terms given. Remember, a sub n minus 1 is the previous term in the sequence, and a sub n minus 2 is the term before that. We've been given the first term, a1, and the second term, a2. And we'll need to find both of those to find a3. Let's try to find it, the third term. According to the formula, a3 must be a2 plus a1. We substitute the appropriate values. Notice that I switched a1 and a2 as that's generally a bit easier with this sequence. We find that a3 equals 2. So here's our sequence so far. Notice that we did 1 plus 1 to get 2. For the next number, the pattern is the same. We'll take the two numbers, the one we just found and the one before that, to get the answer for a4. We have 1 plus 2 equals 3. Next, we'll do 2 plus 3 to get 5, and then this pattern continues. Can you find 4 more? Pause the video and give it a try. 3 plus 5 is 8. 5 plus 8 is 13, and so on. By the way, a formula for the Fibonacci sequence with only numbers and the variable n is really complicated. So if you really want to find a term late in the sequence, you just got to keep adding. As one final question, what's the 8th term in the Fibonacci sequence? If you've written out the sequence far enough, just count up to the 8th one. One reason the Fibonacci sequence is so famous is because it occurs in nature. This is what we call the Fibonacci spiral. Notice how the Fibonacci sequence describes these gray squares' side lengths as they add onto each other. Now, check out this nautilus shell. They match almost perfectly. Isn't that wild? This spiral actually leads to another interesting sequence. Let's look at one piece at a time, specifically at the ratio of its longer side length to its shorter side length. For the first two squares, this ratio is 2 over 1, is 2. For the first three squares, the long side is now the height. The short side is now the width. Regardless, this ratio is 3 over 2, which is 1.5. For the next step, we get 5 over 3, which is about 1.667 repeating. Let's look at one more step. This one is 8 over 5, which is 1.6. Now take a look at these fractions. Pause the video and see if you could determine the next three fractions. You might even look at the big spiral to make it easier on yourself. Here's our sequence. Notice we're really just dividing consecutive values from the Fibonacci sequence. In addition, you can just grab them right out of the spiral. Now let's write the approximate values for these fractions and see if we notice a pattern. They seem to be going up and down, but maybe we should write out a few more terms. It starts repeating. Well, actually it doesn't if you don't round, but there must be something special about 1.618. Let's investigate. Let's look back at the Fibonacci formula for a moment. We're going to perform some steps that may look odd, but watch until the end when we'll discover something amazing. We'll replace the furthest back term, a sub n minus 2, with a 1. The next one, a sub n minus 1 with an x, and the current one, a sub n with x squared. To solve this equation, we will set it equal to 0 and then use the quadratic formula. Simplifying that, we get 1 plus or minus the square root of 5 all over 2. Now, why on earth did we do this? We'll take a look at the approximation of the solution that uses the plus. Oh, wow. That's the same number that we found on the previous slide. This number is called the golden ratio, named by the Greek letter phi. Let's take a look at the spiral again, but now we're going to look specifically at the last rectangle. Do you like this rectangle? I know, that's a weird question, but seriously, do you like it? Here's some other rectangles for comparison. Remember, this rectangle had dimensions 34 by 21, and this ratio was about 1.619, almost phi. This is often called the golden rectangle. It's considered to be the most aesthetically pleasing rectangle, and it appears in many forms of architecture. The golden ratio has been known since ancient Greece, and it showed up in their architectural designs, such as the Parthenon, constructed between 447 and 432 BC. The golden ratio was also used in later architecture, such as Romanesque Cistercian architecture. This is the Senonc Abbé, founded in 1148. The golden ratio is used in some modern architecture as well. Let's look at more appearances of the Fibonacci sequence in nature. The Fibonacci spiral is everywhere. Here's a spiral aloe plant and a fiddlehead fern. We often use the term Fibonacci numbers to describe the terms of the Fibonacci sequence. They show up everywhere too. Here's the top of a pine cone. If you count the spirals in either direction, you'll get two different numbers. Pause the video and see if you can count how many spirals there are going each direction. There are 8 spirals in the clockwise direction, and there are 13 spirals in the counterclockwise direction. Why are these numbers important? 8 and 13 are both Fibonacci numbers. Many flowers, when they have all of their petals, have a Fibonacci number for their number of petals. Pause the video and count the petals on these flowers to check. The first is a buttercup, which has 5 petals. The second is a cineraria, which has 13 petals. The last flower is a pyrethrum, which has 34 petals. That last one was probably difficult to find all 34, but they are all there. Now you can use the Fibonacci sequence. Isn't it amazing how math can occur in nature? You've seen examples of the Fibonacci spiral, found the golden ratio and looked at how architecture has used it, and looked at how Fibonacci numbers appear in many different places. We hope these examples give you a lasting impression and you begin to see these patterns everywhere. Next time, we'll look at 2 more special sequence types, the arithmetic and geometric sequences. See you next time. Hey, hey.